Okay, last time. So pleasure to introduce Duncan Dauvergne for our last talk of the session from Princeton University, who's going to speak about the directed landscape.
Okay, thank you, and thanks very much for the invitation. Yeah, so I'm going to talk about the directed landscape, which is a fairly new object that I constructed in joint work with Janos Ortman and Balint Virag, and it's what it is it's kind of a universal random metric in the KPZ universality class. So I'll start with a kind of simple discrete model of first passage percolation. So just take the lattice set 2, and on every edge put an IID random variable. So this gives a random weighted graph, and you can look at graph distances in this random weighted graph, and you can look at geodesics in this weighted graph as well. So here's an example where the edges are IID equal to either 1 or 2 with equal probability, and there's a geodesic drawn between the 2 corners. And we're going to be interested in understanding the behavior of these sorts of metrics when you take the distances between the points to infinity. Okay. So what should happen for these sorts of models? So I'll look at a pair of points that are sort of order n apart. So if I have 2 points P and Q, and they're order n apart in this sort of model, and you put IID edge weights, non-negative random variables, then this distance is dominated by a mean term, which is going to be like a constant times n, because they're order n apart. And then there's going to be a fluctuation term, which you can kind of check from simulations. This fluctuation term should be like order n to the 1/3. And this behavior you'll always see kind of regardless of what IID weights you choose, as long as you have sufficiently many moments. So slightly more than 5 moments is what you need to see this. Okay, and then the other thing you can look at is you could look at the geodesic here. And what you see is, okay, maybe the geodesic wiggles back and forth between P and Q, but the scale at which it fluctuates back and forth, this is like order n to the 2/3. Okay. So what I'm going to be interested in today is constructing a scaling limit of the entire random metric in some sense. And so we're going to construct this scaling limit on a strip in order to see interesting correlations between distances and the limit. So the main direction on this strip is going to be order n. And the scale at which you expect to see interesting correlations is this order n to the 2/3 scale, because that's kind of the scale at which, say, geodesics from P and Q and geodesics from P prime and Q prime have sort of maybe some chance of overlapping a little bit, but they won't kind of collapse in on each other, and they won't be entirely disjoint in the limit. Okay, so heuristically, you expect something like this. So we want to, so in this, my second coordinate is representing the main direction, that's order n. So that's going to be a time-like coordinate. So I'm going to use the coordinates s and t for that, and then we have a space-like direction which is on this order n to the 2/3 scale. So what you expect to see is kind of what I was saying. You have a mean term, and then you have a fluctuation term, which is going to be a random 4-parameter function L of x, s, y, t. Okay. And this L is the directed landscape. Okay. So for these first passage percolation models, everything that I'm saying so far is kind of purely heuristic, because there's no kind of concrete, nice integrable structure which allows you to prove any of these fine fluctuation estimates. But for other kind of closely related models of last passage percolation, which I'll talk about in a bit, we were able to show that this is indeed the case, that you can that you have a 4-parameter limit, which is the directed landscape. Okay. So just to mention a little bit, some other well-known models in this world. So this is, we're working in the KPZ universality class. And the way I'm going to be thinking about this today and focusing is I'm going to focus on metric models. So first passage percolation, like I just spoke about, and last passage percolation, which I'll talk about in a bit. There's also the directed landscape. You also expect to govern the behavior, the limiting behavior of random growth models. So there's a connection between random growth and random metric models. So Santiago was talking about this. For example, if you look at a growing ball in a random metric, this is a random interface growth model. So things like the KPZ equation, Tay-set, ballistic deposition, these things can kind of fit into this class. Okay. And then there are some models which are maybe one step removed from, or a tiny little bit removed from metric models and random growth models. So these are directed polymers, longest increasing subunits and uniform permutations. All of these things should have fluctuations governed by the directed landscape. There's also some links in terms of limiting distributions you see with limiting distributions from random matrix theory. This is, I'll say a little bit more about this, but it's not, I don't think it's a super strong link. I don't know of a random matrix model that should converge to the directed landscape. So it seems, as far as I understand it, it seems this connection is just above the level of margin distribution. So there is a nice link there. Okay. So let me say a little bit more about this L. So at the simplest level, it's just a continuous function. So it's a continuous 4-parameter function, and you really should think of it as assigning distances between pairs of space-time points xs and yt. Now it has this property, which is it's only going to assign distances to points where the time coordinates s and t are ordered in the right way. Okay, and this is kind of a feature of how the scaling comes from the pre-limiting models. So because you need to subtract off a large mean term, which is kind of a constant times t minus s. So if you subtract off that same constant times s minus t, what you see is that L would have to assign sort of infinite distances if you switch the order of the points around. So it's metric-like, but it's not a metric in that it's not going to be a symmetric function. So it has this directed structure. Another way it's not really a metric is it's going to be able to assign positive and negative values. And there's another thing which is really just a convention, which is that usually it's a triangle inequality for a metric. Here, kind of by a sign convention, the triangle inequality goes in the opposite direction. So this is purely convention. You could set up the whole thing with negative signs, except then you wouldn't see, then you'd see sort of negatives of well-known random matrix theory distributions, for example. Okay, but all this is really to say it's best to think of this just as a random metric on the plane, on a space-time plane where you're kind of only allowed to go in one direction. So you sort of have points x, s, and yt, and you can define paths and geodesics which will move sort of forward in time in this way. Okay. So when thinking about this object, I think maybe the simplest way to think about it is we're just going to start by trying to understand the marginal distribution. So just understand the 1-point distribution. That's the simplest thing. And there are two parts to this 1-point distribution. So the first is a random part. Okay, so the 1-point distribution up to some constant shift is just a rescaled Tracy-Whittam GUE random variable. Okay, and this particular fact goes back to Beik, Deift, and Johansen in the 90s. So that's one feature here. The second thing you'll notice here is this x minus y squared over t minus f. So there's also a deterministic part to the 1-point distributions. And the way you can think about this is if I got rid of the random Tracy-Whittam part and I just saw the deterministic part, that's the scaling, that's the scaling limit you would see if you applied this 1, 2, 3 KPZ scaling to the usual Euclidean metric. So you do this with the usual Euclidean metric, and what you see is this parabola. And so in the absence of randomness, you would see sort of a very simple limit where you can define paths, and geodesics are going to be straight lines. And so you can think of L as retaining the fact that you have this parabolic term means that it retains some sort of memory of the geometry of the plane. So the next thing you can start to do is try and vary it. You can think about what happens when you just vary, just the spatial coordinates or just the time coordinates. Okay, so if you vary just the spatial coordinates, so just x or y, then what you see basically just looks like a Brownian motion. So again, these things have been known prior to the full construction of this object. These particular results, I would say, go back to Corwin and Hammond. And interestingly, or sort of maybe unsurprisingly, the behavior is quite a bit different if you vary these time coordinates s and t. So if you vary these time coordinates, then instead of seeing something that's locally Brownian, you see something that's quite a bit rougher. So it's only Holder almost 1/3. And this, I'm not sure exactly the right accreditation for this result, but there's a paper of Sarkar and Hammond that proves this, I know. And the other thing you can do, I haven't kind of talked about geodesics and paths in the directed landscape in that much detail, and I don't really want to focus on it, but you can define sort of optimal paths through this directed landscape noise. And what you see there is they're actually smoother than both the spatial and temporal fluctuations of the directed landscape. So these geodesics are actually Holder almost 2/3. Okay. So in particular, these geodesics that you see are, they don't look anything like a Brownian bridge, for example, which is maybe your first guess. Okay, so that's a little bit about the object. And for the rest of the talk, I want to get into kind of some of the main points of the construction. So the way we proved the existence of this object is we started from Brownian last passage percolation, which is a really tractable integral model of last passage percolation. Since the paper with János and Balint proving convergence to the directed landscape from Brownian last passage percolation, we've extended this, or Balint and I have extended this to other models like exponential, geometric, Poisson last passage percolation, which have a similar integrable structure. But I like Brownian last passage percolation, so I'm going to stick with this. So the idea is, again, we're going to define kind of a random metric on the plane, just like in first passage percolation, but instead of a noise coming from IID random edge weights, you're going to have a noise coming from a sequence of independent two-sided Brownian motions. Okay, so with these independent two-sided Brownian motions, now you need a notion of path length in this noise. So for us, paths are going to be functions from a real interval to an integer interval. So a path is going to look something like this. I'm specifying that they're always going to be non-increasing. So say I have line n down here all the way up to line 1 up here. The graph of a path might look something like this. So these are my admissible paths that I'm going to allow. And then the weight of the path is just going to be the sum of Brownian increments that you pick up along the path. So you can see, you look at all the Brownian increments, so you pick up all of these independent increments along the path. Okay, so this is a reasonable notion of path length in this Brownian environment. So now you have a notion of path length. You want to define a notion of distance. So the natural thing would be distance between 2 points is the length of the shortest path. Kind of by convention here, we make distance the length of the longest path between a pair of points. Because we're working with Brownian motions and everything is going to be, nothing's going to change if you flip the sign. It's really just a convention in the case of Brownian motions that we choose longest instead of shortest paths. So this is what we call a Brownian last passage value from xm to ym. Okay. And one other thing I'll note about this is that these distances are only defined for points in the right order, because paths, as I drew them, paths can only go up and to the right. So if you have points in the wrong sort of order, you cannot define this distance. But that doesn't affect what you expect to see in the scaling. Okay, so this is, again, this is kind of reiterating what I was saying. But even though there are some, differences which mean this is not a metric, it really is best to think of this sort of directed metric on R cross Z, this space where the Brownian motions live. Okay, so here's our theorem, which looks a lot like this heuristic I put up before. So I have this scaling where I'm going to be looking at lines which are kind of order n apart. So I'm going from negative Sn to negative Tn. So there's a sign flip here for technical reasons. I won't say why. And I'm going to be looking at sort of a window which is order n to the 2/3 in space, as we've seen before. And I'm going to look at Brownian last passage values in this strip. And again, what you see is you have an initial mean term, and then the fluctuation term is governed by the directed landscape. And here I've written some funny. I've written the precise type of convergence here, which is a fairly strong notion of convergence, as in the error term is sort of going to zero uniformly on compacts in distribution. I'll only say this is interesting only from the point of view, or maybe this is interesting mainly from the point of view that because it's a strong type of convergence, you can pass a lot of results from the pre-limit to the limit. So in particular, this convergence is strong enough that it almost immediately allows you to conclude that geodesic, so shortest paths in Brownian last passage percolation, converge to the analogous object in the limit. So not only do you get convergence of the metric, but you also get convergence of its geodesics. Okay, so we're going to think about how you would build this object. And I think the right way to go about trying to construct the directed landscape is to imagine, okay, what sort of limit could we have and what properties would it have to have? And if you think about this for a while, you realize there are certain simple properties that it's going to have. And in fact, it's going to be characterized by these 4 properties, 3 of which are easy and 1 of which is very hard. So the first easy property is an independent increment property. And you can see this property coming from Brownian last passage percolation. So say I look at disjoint time intervals going from S to R and R to T. And I'm thinking about Brownian last passage. So then distances between line Sn and line Rn, say in Brownian last passage percolation, these use one set of Brownian motions, and distances between these next 2 times use another set of Brownian motions. So of course, they're going to be fully independent. And so when you pass to the limit, what you see is that disjoint time intervals have independent. It's kind of a very natural property. The second property is a semi-group property that we call the metric composition law. It's really a metric property. Again, this is something pretty simple. So you can think either in terms of Brownian motions or directly in the limit. So say I want to look at what the distance is between xs and yt. And I have some intermediate time R. So then what I have to do is optimize over all paths from xs to yt, and any such path has to go through some location zr here. And so really I'm finding this optimal location zr, and I'm just going to be adding up a distance from xs to zr and from zr to yt. And so what this tells you is that the distance from xs to yt has to be the maximum overall z of the distance from xs to zr plus the distance from zr to yt. So it's again a really simple metric property essentially. The third simple property is that because it's a scaling limit and because you started with this translation invariant field of Brownian motions, is going to satisfy nice scale and translation invariance properties. Okay, so these are three very simple properties. And the way I think of these is that you should think in terms of an analogy with Brownian motion. So Brownian motion is another independent increment process. Its scale and translation invariant, and its increments satisfy the simple property that if you want to know the Brownian increment from time s to t, it's just the increment from time s to r plus the increment from time r to t. So it satisfies, rather than satisfying a metric composition law, it satisfies a simpler addition law, right? Okay. So the directed land, continuing the analogy with Brownian motion is completely determined once you have these three properties by its distribution of the increment from time 0 to time 1. So just by the normal distribution. Okay. And analogously, L is then going to be determined by its distribution going just from time 0 to time 1. And this object is the Airy sheet. So unlike with Brownian motion, it's no longer just a distribution, it's now going to be a 2-parameter function. And historically, this is really the crux of trying to construct this object. So putting together the object once you have this Airy sheet is not the difficult part, but trying to understand how do you get the Airy sheet, that's quite hard. So I think that was spam. Okay, so I'll say just I don't have too much time to talk too much about the construction of the Airy sheet, but I'll just say kind of, hopefully get to the key idea that goes into constructing it in very brief terms. Okay, so this is where we're going to start to use something special about Brownian last passage percolation, which is Brownian last passage percolation has a really nice integrable structure, which I think of as coming from the combinatorial Robinson-Shenstedt-Knuth correspondence. So this is going to be one presentation of this RSK correspondence, which is the following. So I take n Brownian motions, B1 through Bn, and I'm going to map it to another sequence of n functions, Wb. Okay, so Wb1 up to Wbn, where the Wb's are defined through the following rule. And I need to tell you what this supremum is over. So where this supremum is over is summing up path lengths over k tuples of disjoint paths. So let's try and unpack this a bit. So what is Wb1? So Wb1 of y, there we only have one path. So it's just going to be the largest possible path length from the bottom corner. So it's going to be the largest possible path length from 0n all the way up to y1. And there's a small typo here that should say 0, not y, not x, because there's no x in the formula. So the top path is just a last passage value in Wb. The second path is sort of the additional gain you get from being able to optimize over an additional disjoint path. So you don't do as well as you did with your first path, but you still do pretty well. So you make this gain from adding a second path. And what you see, and you can check this combinatorially, it's not the simplest thing, but it's, if you think about it for a while, you can figure it out, that deterministically, this Wb has ordered functions. So we're taking a sequence of n independent Brownian motions which have no relationship, and through this bijection, passing it to a sequence of functions which have this ordering property and have a nice relationship with last passage percolation. So the other thing about this map is the RSK map has sort of many miraculous features. One feature is when you start with Brownian motions, almost surely you can reconstruct your original Brownian motions from this melon side Wb. So you can go, it's a bijection, you can go from one side to the other and back. This is an almost sure property. You could come up with functions without this property, but for Brownian motions, it's almost sure. And what this means, or one consequence of having a nice bijective structure, is it also plays really nicely probabilistically. So the push forward of the n independent Brownian motion measure is nice under this map W. So WB is given by n non-intersecting Brownian motions. And so you can genuinely start doing analysis on this. There are nice determinantal formulas for this object. It's, you know, also corresponds to Dyson's Brownian motion, random matrix theory. And you can really start to understand this. So we're going to try and take the KPZ scaling limit of WBN. So this was done at the level of finite dimensional distributions. This was done by Prehofer and Schoen, and then later by the version that I'm stating, sort of this uniform on-combat convergence, was done by Corwin and Hammond. And what this says is that if you look at WB and you kind of take a scaling window, which is on this KPZ order n to the 2/3 scale, what you see is a limiting object, which is called the parabolic airy line ensemble. Has a funny name, but I think it's best thought of just as infinitely many non-intersecting Brownian motions. And if you trace through the connection with last passage, what you get is that W1 of y is just the airy, has to be the airy sheet value from 0 to 1. So this gives you like half an airy sheet, okay? And the question is, how can you then vary the other coordinate? And the key to that is the following combinatorial property of the RSK bijection, which we kind of stumbled upon when thinking about this stuff. It turns out it goes back a bit further to these two groups of authors. And what it says is that last passage from the bottom to the top line is preserved by this map from B to WB. Okay. So this suggests the following really loose strategy for trying to construct the area sheet. So this last passage from the bottom to the top line, this should converge to the area sheet. This is what we want. And this should occur in this KPZ scaling. And we know that WB converges to the airy line ensemble in the KPZ scaling. And so what you might hope is that maybe this equality can somehow pass through to the limit, and that you can express S of xy as some sort of last passage problem across the airy line ensemble from x infinity to y1, we'll call it. So this is sort of this dream formula that you might hope to get. And this is what we do. We find out a way to, we figure out a way to make this rigorous. And this is kind of the hard part, and I don't have any time to say anything about it. So I will go ahead and stop there.
Let's thank Duncan. And we have time for some questions.
So, may I ask a question?
Mm-hmm.
So this representation with the non-intersecting Brownian motions, does give you a realistic path or way to prove convergence for other models, or does it maybe a little bit too optimistic to do?
So it works for a few other special models. So this representation as non-intersecting Brownian motions, there are, I think, maybe 4 other models where you can start with a last passage problem, pass it through essentially the same correspondence, and you get non-intersecting something. So if you start with, so you can get non-intersecting, if you start with exponential last passage percolation, you get non-intersecting exponential random walks. You can do this with Poisson last passage percolation to get non-intersecting Poisson walks, and you can get non-intersecting geometric walks. There's also sort of a slight variant which allows you to get non-intersecting Bernoulli walks. But it really is, it works in those, I guess, 4, maybe there's a 5th case if you think about it a bit, but it's certain principle. It's something very, yeah, it's really quite a special property.
Other questions?
I have a question. It's perhaps unfair question, because everything here is in 2 dimensions. So you're really in the KPC universality class, but I always wonder if you think that there could be an analogous object in other dimensions, or is it a dimension where it becomes trivial, perhaps?
I'm not sure. I think there's, it's not something I've thought about too much. It's really hard. I mean, the fact that, there's this huge reliance on non-intersecting locks really suggests, I mean, you have this, it really suggests that you're using this two-dimensional property that, two paths in the plane have to cross. If you put
Yeah, so you use planarity, but it's not obvious, I guess. It's kind of maybe hidden, but not clear if it's essential or not.
So certainly, if they're in higher dimensions, the scaling exponents will change. It's kind of quite, I would say it's quite clear that the scaling exponents have to be the same. I'm not sure if there is sort of some upper dimension at which point everything will become trivial. And I'm not sure what that would quite like. Again, it's not going to become trivial in a trivial sense. But yes, there might be, there might be some. Okay, so for example, kind of what I mean is, if you look at the scaling limit of geodesics, the scaling limit of geodesics in 2 dimensions are these polar 2/3 minus paths. I'm not sure, say, if there is a dimension at which the scaling limit of geodesics is just Brownian motion or a Brownian bridge. That's possible, and I wouldn't be. Yeah, I don't know, but it's not something I've thought about.
No, but there's work at the level of, say, the KPZ equation. So not the geodesics, not at the level of the geodesics, but at the level of the scaling of these limits, and those I think are clearly Gaussian from dimension 3 on.
Yeah, but well, even if you know, I mean, the finite dimensional distribution, there's still the problem of building the whole landscape.
So the class becomes trivial in the sense of Gaussian for D bigger than or equal than 3, and I think 2 as well, but there may be some.
Yeah.
On that note, Daniel, so in 3-dimension higher, there's a phase transition in temperature. So what you're talking about is the low temperature region. But in those dimensions, if you go above the critical temperature, there should be a strong coupling fixed point.
Right.
Great. Oh, thank you.
Okay. Any other questions for Duncan? I have hopefully a quick question. How strong is the convergence of the geodesics that you get?
It's uniform convergence.
So it's just, I mean, everything passes through?
Yeah, it's almost purely topological. So once you have uniform on, like if you set up a coupling where the metrics, where the pre-limiting metric converges uniformly on compact sets to the limiting metric, then you can show, and you have like that's all you need. Then you can show that all geodesics will converge uniformly as long as the limiting geodesic is unique. So you could have a situation where you have sort of 2 limiting geodesics, and then maybe you get some flip-flopping back and forth between 2.
Right. So that's the extra work of really constructing the unique and showing that it's unique. Right?
Yeah.
Okay.
Yeah. Showing that the limiting geodesics are almost surely unique is quite easy, because this is just like showing. This is basically amounts to showing that an Airy process has a unique maximum almost surely. So this kind of this work is already done in some sense.
Right. Okay. Thanks. Okay. Any other questions? If not, let's thank Duncan for the very nice talk, and all the speakers of today and of the session. And thanks everybody for coming. And that's it, I think.